Welcome to Maths with EJD. In this video, we're talking about convex optimization. Generally, we can group convex and non-convex optimization together and see how that goes. So, um, first of all, an overview of what convex optimization is about. Overview. Okay. So, convex optimization is a subclass, is a subclass of optimization problems where the the objective function is convex and the feasible region and the feasible region is a convex set. The feasible region is that place where you can find your solution. The solution you're looking for is a convex set. Okay. These problems, these problems are significant because they guarantee they guarantee a global optima, which makes them more tractable than general optimization problems. Okay. The beauty of convex optimization is that you can be sure if you're looking for a global minimum or a global maximum, you can always find it. But in the case of non-convex, that's another ballgame entirely, as you're going to see later. So let's talk about the key concepts in convex optimization. So the first thing is the convex sets themselves. What are convex sets? Okay. So we say that a set C is convex if for any if for any 2 points x1 comma x2 belonging to big C, the line segment the line segment joining them entirely 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 lies within C. So that is for all lambda belonging to 0 comma 1. Okay. Uh, Lambda x1 plus 1 minus lambda x2 totally belong to the set C. Okay. The possibility we are talking about here is that you have, say, imagine this is a very good example of a convex set. So if you draw a line joining this convex set from here to here, so you see the line totally lies within that interval. So on the other hand, imagine you have something like this. Uh, so you have something like this, and then you have a line going this way. So you can't surely say this is convex. Of course, this part is convex, right? Um, okay, maybe this is not a good example. Let me try to see another one. Um, let's say, should I say this? Let me look for a good example. Say this, and then you have you have a line. I guess I'm not doing it right. Okay. Um, let me see. So if you have this, for instance, so you can see that if you follow this line all through in this function, so the line belongs to a party, this part, it belongs to another part here. So unlike this one where the line joining the whole convex set totally lies within this, you can't say the same of this situation. When we get to convex sets, we have a clearer understanding of that for sure. So still on the key concept, right? We've talked about a convex set. The next thing is a convex function. So number two concept is about convex function. So a function, f of x is convex if for any 2 points, x1, x2, belonging to Rn, the following inequality holds. The following inequality holds. So it means that if you have to prove that if whether a function is convex or not, you can invoke this inequality, and that is that f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. All right. So if you can prove that a function obeys this, then you can say the function is convex. So so you see, that's the condition for a convex set here. So you just put it into a function, and if you can put it into the function and the function evaluates such that it is less than or equal to lambda of f of x1 plus 1 minus lambda of f of x2, then you can actually say that that function is convex for all lambda belonging to the interval 0, 1, like that. So that goes as far as convex function is concerned. Then we go for number three, where we talk about optimization problem. Of course, it's not the first time we're talking about optimization problems. So in fact, everything we've been talking about under this playlist has been about optimization. So the typical convex optimization. So now the focus is on convex, right? The typical convex optimization problem can be written as minimize the value of x, minimize the value of f of x, minimize x that suits that, right? Subject to gi of x less than or equal to 0, k, where I is equal to 1 to all the way down to m. And then we have hj of x equals 0. That's equality constraint now, where all the j's are from 1 to all the way down to p. Then here, where f of x is convex, gi of x, f of x is convex, and gi of x are also convex functions. They are convex functions. Those are the inequality constraints. Inequality constraints. Okay. And hj of x are affine functions. They are affine functions being equality constraints. Being equality constraints. So that's the general case for convex optimization problem. So let's look at a worked example. Let me switch gear here, and then this can go to say this or even this. Okay. Now, example. In fact, I'll be taking two examples here. So I'll be taking a one-dimensional example first of all, where just x, and then I'll be taking x and y. That's two-dimensional. So example one, if you like. Example one. Okay. So consider consider the following simple convex optimization problem, which is to minimize f of x, which is equal to x squared plus 4x plus 5, and x is greater than or equal to 0. Okay, so that's the problem right there. But before we even go, see that this function x squared plus 4x plus 5 is actually a it's a convex function. That is x squared plus 4x plus 5. Now, the reason why it's a convex function is that imagine if you now have a line, say, which line can I draw here? Let's say um x plus y is equal to 4. Okay, so you can see that x plus y equals 4 is a line that cuts through. So you see the line totally lies within that function. So in that case, you say that that function is actually a convex function. So it means that any solution, and again, another beauty of this is that if you're looking for the minimum value, we want to minimize that function, right? So if you are looking for a minimum value of this function, we can already see it at this tip here. So at the minimum value, x is minus 2 and y is like, I think y is 1. X is minus 2 and y is 1 for this particular function. So it's even clear from the graph itself. So if you're solving this, we already know that there's a global minimum like that. Of course, this is a simple problem. We can even do the global minimum without having to go through this sophisticated method. But the method is just to drive home the point, like we always like to do. Okay. So let's look at the solution step by step. The first thing we want to do here is look at the objective function. Objective function. Okay. The objective function is such that is f of x, right, equals x squared plus 4x plus 5. And what we need to do to determine if this function is convex, we compute its second derivative. Okay, let me write that. To determine if this function is convex, we compute its second derivative. That's how to know whether a function is convex. We compute its second derivative. Of course, you can not compute second derivative without first computing first. So, you have f of x is x squared plus 4x plus 5. So f prime of x, first derivative will simply be 2x plus 4. Then f prime prime of x, that second derivative is simply going to be 2, right? So we see here that so we see we have 2 as a value there. So under this, the next thing we want to talk about is the constraint. So that's the objective function. So the next is the constraint. 2. We have the constraint. So the constraint from the problem originally, we have only one simple constraint, which is x is always non-negative. So the constraint is x greater than or equal to 0. Okay. Which defines a convex feasible region, a convex feasible region, a convex feasible region that is the non-negative, real line. Okay. And then we talk about the solution. The solution. So the objective function, I've assumed before I showed you the graph, the objective function f of x equals x squared plus 4x plus 5 is a parabola, opening upwards, like you saw there, opening upwards. And we can find its minimum, like I told you. In fact, we can see the minimum on the graph already. We can find its minimum by taking by taking the derivative and setting it and setting it equal to 0. Okay. I mean that it can be that simple, very simple, because of course we know f of x, like we've just done, is x squared plus 4x plus 5. Then first derivative, you have f prime of x equals 2x plus 4. So if you set uh, so if f prime of x is equal to 0, so you have 2x plus 4 is equal to 0. So that means that you have 2x uh equals minus 4. So x is equal to minus 2, like we already saw there. So in that case, we can now, if you now do f of 0, so that will be 0 squared plus 4 into 0 equals 5. So what this tells us is that thus the minimum value of f of x subject to x greater than or equal to 0 is 5. Okay, because x cannot be minus 2, because x has been guaranteed to be non-negative. So x cannot be minus 2. So the least we can now take, so because x cannot be minus 2, that is why we now come for f of 0, which is 5, right? So the minimum value of f of x subject to x greater than or equal to 0 is 5, right? It is 5. Um, and and it occurs at x equals 0. It occurs at x equals 0. Okay. So we see that convex optimization problems like this example above are easy to solve due to properties of convex functions and sets. So the global minimum can be found efficiently, and this makes convex optimization a powerful tool in fields like machine learning, operations research, and economics. In the next video, I'll do a two-dimensional problem that involves x and y. So for now, I think we can stop here. Um, so you can take practice questions like this. Practice questions, very simple ones. Okay. Say, um, solve or find the minimum of, uh, say, x squared plus 5x plus 6. Okay. Subject to x greater than or equal to 0. So we want only positive values, basically. So let me see your answer in the comment section. And also, I mean, this is so simple, I don't even have to worry about Python code. But I'm going to do Python code for the two-dimensional one. So we'll see to that pretty soon. Okay, so let me see your comment either on Facebook or on YouTube. And of course, if you have subscribed, thank you so much for that. If you have not, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Don't also forget to like and share so that more people can have access to this. So if there's a problem you'd like me to solve or a topic you'd like me to teach, also let me see in the comment section. Till I come your way again, keep doing much right. Bye.